Alright, in this video we're going to learn about a new distribution. We're going to be comparing the variances of two populations. So let's start with that. Suppose we have two populations and we know that sigma 1 squared equals sigma 2 squared. So the population variances are equal. And each population is normal. Then, for sample variances, S1 squared and S2 squared we have that the sampling frequency, I should say the sampling distribution, so if we set up S1 squared divided by S2 squared, this fraction forms an S distribution. And for this, we're going to be looking at the numerator and denominator of that fraction. So we will use dfn is the degrees of freedom in the numerator. And dfd is the degrees of freedom in the denominator. Furthermore, the F distribution of curves is not just one type of curve. But a family of curves. So, to give you an example of some of these things it could look like, here's the sketch of a few graphs of them for various degrees of freedom in the numerator and denominator. Here's one type. It comes in, starts at 0, 0, and looks like what we were just studying before. Here we have dfn equals 3 and dfd equals 11. So the degrees of freedom are what control the shape of the graph. And that's what we're going to be looking at for this. Although the shape won't be that important, more so the pictures in the back, not the pictures, the tables in the back of the book will be important. Now watch this next one. It comes in curved like this, and then goes like that, like a chi-squared a little bit. Here, this was the case where dfn was equal to 16, and dfd was equal to 7. And then this other one is what really breaks it open as far as the types of curves. Check this one out. It goes like this. And that was when the degrees of freedom in the numerator was 1, and the degrees of freedom in the denominator was equal to 8. Now, no matter what, the area under the curves is always 1. Now, one thing to make your life a little bit easier is the following standard that we're going to use throughout. Whenever I write this like so, we always want S1 squared to be greater than or equal to S2 squared. If you always do that, then the value of f is always greater than or equal to 1. And what that means is we're always going to be dealing with a right-tailed test for every single one of these problems. So keep that in mind. If you set up your structure like this, where S1 squared is the bigger of the two, always set it up that way and you'll be all right. The reason why is these tables are so extensive and so complicated that we're trying to make it halfway easy on you by making you do this first. I'll show you. Wait till you see the tables to see what I'm talking about. So we'll start right off on the tables. Find the critical f value for a right-tailed test where, let's see, alpha equals 0.01. The degrees of freedom in the numerator is equal to 2, and the degrees of freedom in the denominator is equal to 11. So I don't know, right off the bat, I don't know what the graph looks like. So it probably doesn't hurt to always just draw a shape like this and just forget about what the various shapes look like and just concentrate on these tail ends like we normally do. So in this case, with alpha equals 0.01, as normal, I'm talking about that tail end over there. And what I want to find out is this f sub 0 number. Okay, here is the beginning of such tables. As you can see, they're sideways because they're too long to put straight across. And if I look here, I see my alpha is 0.05. We want alpha equals 0.01. So I'm going to have to flip to another page of the tables. So it's broken down by alphas. Let's see what the next alpha is. Here, alpha equals 0.01, which is what we wanted. Now let's go back and see what we have. The degrees of freedom of the numerator is 2, and the degrees of freedom of the denominator is 11. Let's come back to the tables. So the numerator are located across the top of the table, and the denominator are across the side of the table. As you can see them right there. So I want the degrees of freedom of the numerator to be 2. So I'm dealing with this column right here. And the denominator to be 11. So let me see if I can stop 2 and 11. Right there, you see it? This guy that I'm hovering over here. That is 7.21. Let's do another example. Find the critical F value for a right-tailed test with alpha equals 0.025. The degrees of freedom in the numerator is equal to 7, and the degrees of freedom in the denominator is equal to 3. So let's pop back to our tables, and I'll try to find alpha equals 0.025. As I say, that's the way they do it. So here we have alpha equals 0.01. Let me go to the next page. I know I've done 0.05, 0.01, and here we have alpha equals 0.025. So let me get it in view. We want the degrees of freedom of the numerator to be 7. So there we have 7 right there. So I'm going to be looking down this column. The degrees of freedom of the denominator has to equal 3. Let me expose more of this table here. So here's 7, and then 3. Here's 3. Let me move across until I get to 7. 7, there it is. I'll kind of circle around it. 14.62. Let's do another example. Find the critical F value for a two-tailed test with alpha equals 0.1. The degrees of freedom in the numerator equals 24. And the degrees of freedom in the denominator equals 28. Now, as I said, you're always going to be doing a right-tailed test. Not exactly the way I said it. You're always going to be doing a right-tailed test, even in situations like this. What you're going to do is you're going to take alpha and divide it by 2 like you normally do. 0.05. But that's it. You're still going to be doing this. I don't know what the graph looks like, but here we're going to have 0.05, and this is the guy that you're looking for. I don't care about the left one. All I care about is the right one. So let's go ahead and find out what that is. Let me come back to my table. So I'm actually going to look in the 0.05 table. Come back to my tables. I think it was 2 pages before this. There's 0.01. There is 0.05. Actually, I have it wrong. It looks like it's 0.005. I want just 0.05. I went a little bit too far. Let's come for 0.01, 0.025. There's 0.05. Now, I want the degrees of freedom in the numerator to be 24. Oh, lo and behold, there is a 24 right there. And the degrees of freedom in the denominator to be 28. So let's see if I can expose. See, it's up. I'm running out of space. Here we go. So this is even runs off of my screen. It's too far. So I'll have to try to be good about this. I need 24 for the degrees of freedom of the numerator, but 28. See this? It's on a blue band. 28. If I can just follow this up here, I can probably get to it. There's 2.12. Let me use my arrows. 2.04, 1.96. I think I got it. See right here. I'm covering it up right now, but as I move off, see it? It's 1.91. That was 24 and 28. Once again, 24 and 28, 1.91. Scroll down. The hardest part is to make sure that you're in the right blue area as you do it. And in fact, that is there. So we have F naught equals 1.91. And for the last example in using these tables, find the critical F value for a two-tailed test with alpha equals 0.05. The degrees of freedom in the numerator is equal to 27, and the degrees of freedom in the denominator is equal to 19. Now, since it's a two-tailed test, I automatically know that I need to do alpha over 2. That's 0.025. And now let's go to the table and look up alpha equals 0.025. I think that was before where I was, so let me go back to that. There's 0.05. Here's 0.025. So I got 27 in the numerator and 17 for the denominator. So right here you can see there's no 27. It goes from 24 to 30. Luckily, 27 is exactly halfway between the two of them, so I can do this business where I take two values and take their average. Let me see if there is a 19 row. I see the 19 row. Degrees of freedom in the denominator is 19. So what I do is I'll let my cursor stay on that row, or it looks like a column since I'm from here, and I'll simply move my page underneath of it until I get to the two values. Here you can see them, 2.39 and 2.45. I want to take the average of those two because the 27 was exactly halfway between 24 and 30. So 2.45 and 2.39. So you take the average of those two spots, and you end up with 2.42. So that takes care of, I think, all the different situations you can encounter in on the tables in the back. Unfortunately, when I go into the calculator, let me pop this up, give it a second while it comes up. If I go to, where was it, distribution, second distribution, near the bottom of the stack, I'll go to that, you can see that we have an option 0, I have an FCDF. That gives me an area. That doesn't give me a number. It doesn't give me a point or a critical value. And the FPDF is something else entirely. So you notice there is no FINV. There's no inverse F that tells me how to find the F naught. You're going to have to use the tables for that. Now, if I'm calculating areas, I can use this FCDF, but that's not probably what we're going to be doing for the most part in this. We'll use that for p-value situations, but there's another way of doing that anyways. a two-sample f-test is used to compare two population variances. Let's call them sigma 1 squared and sigma 2 squared. So what are the things we need? The samples are random and independent. Each of the populations has a normal distribution. Our test stat will look like this. And we'll always force it so that S1, the numerator, is greater than or equal to S2. That way the F values are always at least 1. Furthermore, the degrees of freedom in the numerator is equal to N1 minus 1, where N1, of course, is the population of the size of the sample from population 1, and the degrees of freedom of the denominator is equal to N2 minus 1, where, of course, N2 refers to the size of the second sample. Now, when we run a hypothesis test, we have the normal business. For this, like normal, what do we normally do first? List H0 and HA. The other stuff above, where where you have to check to see if the populations are normal and all that, that will usually all be assumed in the problem. Then you list alpha, and I've covered this up before. Degrees of freedom in the numerator is N1 minus 1. Degrees of freedom in the denominator is N2 minus 1. Determine the critical F0 number. As I've written above, the test stat F equals S1 squared over S2 squared. I can't say it enough. S1 squared needs to be greater than or equal to S2 squared. And then last, make the decision. Example. Suppose we have the following claim. Sigma 1 squared equals sigma 2 squared. So here we're proposing that the two populations are equal to each other. Here's what my sample stats are. We have S1 squared equals 310. S2 squared equals 297. I like what I'm seeing right now because the S1 squared is bigger. N1 equals 7. N2 equals 8. Let's test the claim. at alpha equals 0.05. So for this, let me put what my H0 and HA would look like. As usual, the equals goes into H0. HA would be that sigma 1 squared does not equal sigma 2 squared. And here this is a two-tailed test. However, it means a little bit different here. What we're going to do is we're going to take our alpha and divide it by 2 to get 0.025. Keep that in mind. Now, the degrees of freedom in the numerator equals n1 minus 1. In this case, n1 is equal to 7. So 7 minus 1 equals 6. The degrees of freedom in the denominator is n2 minus 1. That equals 8 minus 1, which equals 7. So I've got my degrees of freedom in the denominator, the degrees of freedom in the numerator. And so now let's get our critical value. So what does F0 equal? So let's use alpha equals 0.25, DFN and DFD. I got everything I need. And I'm already on the 0.025. So I've got 6 and 7. 6, I see the 6 there for my numerator, and 7 for the denominator. So let me go up to 7 row / column until I get to the 6 up here. I see that the number I want is 5.12. So I'll make a picture. It doesn't matter, the picture's not that important. I have my 5.12 will be out here somewhere. And now let's do our test stat. Here we do F equals S1 squared divided by S2 squared. And when they gave it to us, they didn't give us the standard. They gave us in the right way because they gave us the variance. They didn't give us standard deviation, so I don't have to square these numbers. I can put it in 310 and 297 just like that. And that is approximately 1.044. And that number, as you can see, is way over here. So do not reject H0. We don't have any reason to believe that these variances are not equal to each other. Now, we can do the same thing using p-values with your calculator. For this, let's bring out the calculator, turn it on, and what we're going to choose is go to, let me quit this. I don't like to be in the middle of something, so we'll go there, go to Stat, and then choose Tests. Now, it's near the bottom as before. Let me see which test it is. There it is. See letter E, 2SAMP F test. So we want, let me write this down so you can refer back to it. We're going to do stats. And then we're going to choose tests. And then letter E, which is the 2SAMP F test. Now when we go into there, hit enter to get inside of it. You can either use your data or you can use the stats that are given to you. In our case, stats were given to us, so I'm going to highlight stats. Unfortunately, they gave us variance and not standard deviation. They told me the variance of sample 1 was 310, so that's easy enough. I'll just take its square root. You don't have to leave this screen. You can simply write 310 in here. You don't even have to finish off the parenthesis. It'll do it for you. So it puts the number in there. You don't put the degrees of freedom, just put the size. So we had 7 and 8. So let me put 7 for N1. That SX2 was going to be the square root of 297. And your way out of that. And so it's got those numbers for us. N2 was equal to 8. And then since it's a two-tailed test, we want the not equal to. So you can enter your way out of that. I think you need to arrow your way down because it won't actually enter your way through it. And then enter for calculate. And you can see that it gives us the F value that we calculated before, about 1.044. So it will find that. It will find the test stat for you. And then it will give you the P value, which is 0.941, let's say 0.942. So P is approximately equal to 0.942. And alpha, the original alpha, what was it? Alpha was 0.05. So we can see P is quite a bit bigger than alpha. P is greater than alpha. Do not reject H naught. All right, here is a regular type of an example that we could be looking at. We're looking at a manufacturer, an automobile manufacturer claims that the variance of the fuel consumptions for its hybrid vehicles is less than the variance of the fuel consumption for a hybrid vehicle of a top competitor. So a sample of the fuel consumptions of 19 of the manufacturer's hybrids has a given variance, and then a sample of, so let's take a look at the manufacturer. So we'll look at the manufacturer. What do we have there? We have, we'll call it N something. I don't know if I'm going to call it N1 or N2 just yet, because I want to make sure that S1 is the top one. All right, so N is equal to 19 and has a variance of 0.21. So sigma squared equals 0.21. And now let's take a look at, and I made a mistake there. That is the sample variance. And now look at the competitor. How many of those did they pick up? N for them was equal to 21, and its variance was 0.34. So S squared equals 0.34. So quick look, I see that this S squared is bigger than this S squared. So that means that I'm going to make this the 1 and this the 2. All right, so the manufacturer is claiming that theirs is less than the competitors. So let's take a look and see what this looks like. H naught, HA. They are claiming that sigma 2 squared is less than sigma 1 squared. So sigma 1 squared is greater than sigma 2 squared. This is why you got to get the 1 and the 2 correct at the beginning. Now, you reverse the inequality and include an equals under it for H naught. So I've made everything line up just right. Now, we are going to be using alpha equals 0.10. I don't need to divide it in half because this here is a right-tailed test, which is exactly the way you want to structure all of these. If you always make sure that the S1 is on top, you're always going to be dealing, well, I wouldn't say that, not always with a right-tailed, yeah, you will. You'll always be dealing with a right-tailed test because you're always going to be putting sigma 1 squared is probably bigger than sigma 2 squared, just like this. So let's first look for the critical value. Let's see the degrees of freedom in the numerator. Remember, the ones go in the numerator. So that's 21 minus 1 equals 20. The degrees of freedom in the denominator, which will be over here, will be 19 minus 1, and that will equal 18. Alpha is equal to 0.10. Let's go ahead and find out what f sub 0 is. And as before, I don't care really what the exact graph looks like, so long as I get enough for me to make a decision. So we're looking for this spot here. As usual, that amount is 0.10. So let's go to the tables and look up my f naught. All right, if you scroll through enough of the pages in the back of your textbook, you'll eventually get to alpha equals 0.10. Now I need the degrees of freedom of the numerator to be 20, which I see up here, and then I need the degrees of freedom for the denominator to be 18. So let me find the 18 first. Okay, so 18 is here in this blue band that I'm going up along. And then let me scroll underneath of it until I get to 20. So it looks like I got it. 1.84 is my f naught value. And my test stat is f equals s1 squared divided by s2 squared. S1 squared was 0.34. And S2 squared was 0.21. So when I do this, I get approximately 1.619. And you can see that that is just right outside of the critical region. And so we do not reject H naught. So in fact, the claim is not looking like it was actually true. All right, for the p-value method, let's see what we have. Let me go into my calculator. Let me go to Stat, Tests, choose letter E for the 2 sample test. We'll use stats because I've been given the stats. Now, I don't want to put in 0.34 because remember, this calculator requires that you put in the standard deviation, not the variance. So I have to take what they gave me and take its square root. So let me get 0.34, enter my way out of it. N1 was 21 like I have. N2, I need to take the square root of 0.21. Enter that way out of there. N2 is equal to 19. The way we set it up, we want this greater than sigma 2. Actually, we want sigma 1 squared greater than sigma 2 squared. But if we know they're both positive numbers, then this absolutely means that sigma 1 is greater than sigma 2. And then go down to calculate. And let's see what you get. There I get my f stat, my test stat again, 1.619. But I'm more interested in the p-value here. I have 0.154. So p is approximately 0.154, and alpha was equal to 0.1. So since p is greater than alpha, we do not reject H naught. All right, here we have an example that will require us to enter data. So I am going to put the data into the calculator just as we see there, and I'm going to use L1 for golfer 1 and L2 for golfer 2. So let me go ahead and get that data in there. Grab my calculator and go to Stat and Edit as normal. And as usual, delete until you get rid of all the data that's there, or refer to an earlier video just to clear out the L1 and L2 real fast. But I think this is the most convenient way. And let me go ahead and start putting in my data. All right, I've got my data in there. Let me go back to what the question is asking before I do anything else and set up my alternative hypothesis and null hypothesis. So let's take a look here. The table at the left shows a sample of driving distances in yards for two golfers. At alpha equals 0.1, can you conclude that the variances of the driving distances differ between the two golfers? Well, this is easy. This is not a left or right tailed test. This is a two-tailed test. So can you conclude that the variances of the driving distances differ? That's the key word here. So sigma 1 squared does not equal sigma 2 squared. That's the claim. The way I said, I don't know why I said that, but let me fix it on the second one. The claim was in HA. The not equal always goes into HA. So let me take the claim out of that spot. Now, let's look at our sample variances and see what we have. To get the sample variances is very simple. All you have to do is go to Stat, go to Calc, choose two variable stats, and once you hit Enter, you have your X list and Y list. If you want X list is like L1, Y list is like L2. Enter your way out of this thing. And first it will give you X. All I really do care about is S sub X, is 13.0282. So we'll call it S is approximately 13 point, let me have you back, 0282. And then let me go ahead and square it. And then the other one, I'm waiting to call which one S1 or S2 depending on how this shakes out. So let's pop into the calculator for S, the second S, which will be listed under the Y's. There it is. 4.8178. So now, based on this, since I see that the left S is bigger than the right S, I can put my 1 here now. And I was way too excited. I shouldn't have done that. I need to take this and square it. Here, I'll probably round to 4 decimal places. Let's take care of that one. As I recommend every time, quit the application you're in first before you go and start doing anything else. Then square it. Enter. Let me see. I have 169.734. And then for the other one, and let me square that, 23.2112. So my test stat, that's F equals S1 squared divided by S2 squared. Let me see, what do we have? I have 169.734 divided by 23.2112, and that gives us approximately 7.313. Now, for this is a two-tailed test. And so, with that in mind, we are going to use alpha equals 0.1, so alpha over 2 equals 0.05. The degrees of freedom of the numerator was equal to 10 minus 1, which is 9. The degrees of freedom of the denominator was also equal to the same amount. So 9 and 9. So the table I want to look up 0.05 and 9 and 9. All right, so here I am on the table. 9 and 9. Let's see where you're at. There's 9. Let me go up that row / column until I get to 3.18. 3.18. And we can see that our test stat is buried deep into there. And so we reject H0. That means it does look like their standard deviations or their variances are actually different from each other. Now, to finish it off, let me do the p-value method. And for that, the beauty of this calculator, or one of the beauties of it, is you can go to stat. I know I speak ill of it sometimes, but other times I speak well of it. Go to tests. Let's go up to letter E for the 2SAMP-F test. Enter. You can now use your data that I've put in to L1 and L2. See how they have it? Frequency list 1, L1, frequency list 2, L2. If you should find that the standard deviations were swapped, then you can simply change this right here. In fact, I don't believe that your calculator is under so much stress that you have to put S1 on the numerator or not. I think it'll handle it either way, although I've not looked to see how that will work. So I wouldn't do it unless you're willing to watch some YouTube videos or something that will explain how it works. So anyways, the choice here, obviously, we have a two-tailed test, so get rid of the sigma 2. So let me put enter there. You have to enter. You can't just enter your way through this thing. You actually have to make choices as you go. And then finally, let's calculate our p-value. Once again, there's the test stat, 7.313. Our p-value is approximately 0.007. And alpha, remember when you do this to use the original alpha, we can see that P is less than alpha, which tells us to reject H0.